In the last few lectures, we have been discussing about the medium scale integrated circuits, what we call as MSI circuits, and we took a look at one such circuit, that is the multiplexer, or it's a block which can be used to realize functions of more complexity which need not involve the use of so many gates as the starting point. So when we talk about the mux or the multiplexer, what we see is that there are multiple data inputs. Then there are select inputs, which are essentially the same as the number of variables in the logic function. And there is one output. So all said and done, if you are using one multiplexer, you can realize one logic function because it has one output. The question now comes is there any way through which we can use MSI circuits to realize multiple logic functions without increasing the circuit complexity too much? So therefore, the answer is indeed yes, but we cannot do that so easily using the mux because the mux has only one output. So therefore, technically speaking, you can only realize one logic function using one mux. So to realize more number of logic functions without making the circuit too complex, we introduce another MSI circuit block that is essentially the opposite of the mux. The opposite of the mux or the multiplexer is called as a decoder. Sometimes it's also called as a demultiplexer. Although the word decoder is more popular. So how is it different from the mux? Well, first of all, a mux has multiple data inputs and multiple select inputs. Decoder is just the opposite. Decoder has the same select inputs and it has multiple outputs. There is no concept of a single input of a decoder, as you would expect if you were building something that was the literal opposite of a mux. So these are there, the select inputs and the multiple outputs. So therefore, if there are n number of select inputs, then the number of outputs would be 2 raised to n, which is kind of like the data input and the select input relation in the case of a mux. So generally, for a mux we write something is to 1 mux, that indicates the number of data inputs to the number of outputs, which is usually 1. In case of decoders, a decoder is represented using n is to 2 raised to n. So you can have a 2 is to 4 decoder, you can have a 3 is to 8 decoder, and so on. So let us start by taking the example of a 2 is to 4 decoder, which in terms of understanding should be expectedly pretty close to a 4 is to 1 mux. That is the one with which we had started our discussion initially a few lectures ago. So when we look at, let us say, a 2 is to 4 decoder, it looks like this. Some notations show this as an inverted trapezium to show it as an inverted mux. So there are 2 select inputs and 4 data outputs. So therefore, let us say there are two inputs A and B, and the four data outputs, we'll call them as Y0, Y1, Y2 and Y3. Now let us see how this works. The decoder so far looks pretty much like the opposite of a mux, but in its functioning it is slightly different, and let us see how. Now there are four outputs, Y0, Y1, Y2 and Y3, two select inputs. Now, what happens essentially is that depending on the select inputs, one out of these four output lines is activated. Now, activated means what? If A and D is 0 and 0, then Y0 is activated and it becomes 1, where the rest of the outputs at the same time are all zeros. Okay, so when A and D is 0 and 1, Y1 is activated. That means Y1 becomes equal to 1 and the rest of the outputs remain 0. When A and D are 1 and 0, it is Y2 which becomes 1 and the remaining inputs are 0. Likewise, for 1, 1, it is Y3 which becomes equal to 1. So, in this case, what you see essentially is that whatever be the value of A and B, any one of the outputs is 1 at any given time. So therefore, this output or this kind of decoder where the activation of the output is indicated by a 1 is called as an active high decoder or active high output decoder. Because activated output is indicated by a 1. So, an active low output decoder also exists. Let us see what it looks like. So again, let us see. Let us not draw the inverted trapezium symbol of the decoder. Again, it is a 2:4 decoder. Two select inputs A and B, and there are four outputs. But this time, the outputs are indicated with bubbles, which is similar to a NOT gate, but it's not. These bubbles just indicate that the output is active low. So Y0, Y1, Y2 and Y3. So in this case, the truth table would just be the opposite of what it was earlier. Alright, so over here, when A and D are 0 and 0, Y0 gets activated. Now in this particular scenario, the definition of activation changes. The activated output becomes 0 and the rest of the outputs remain 1. It is the exact opposite of the earlier case, which was an active high output decoder. When A and D are now 0 and 1, Y1 becomes 0 and the other outputs become 1. When A and D are 1 and 0, Y2 becomes 0 and the rest of the outputs stay 1. And likewise for A and B becoming 1 and 1. So, this is what the basic principle of operation of a decoder is. Whether it is active high, whether it is active low output, doesn't really matter. So just the converse of the previous case, you see 1 out of the 4 outputs becomes 0. So an active high output decoder can also be called as a 1 out of n decoder, and an active low output decoder can be called 0 out of n, or 1 out of n being 0 decoder, where n maybe is capital N, which indicates the number of data outputs. Anyway, those names are not very important. That is just a small piece of information. Now let us see how we can use these decoders to realize some logic function. Now let us say I have a logic function which looks like this. Looks like this, let us say. Something like this. Now I want to use an active high output decoder to realize this function. So therefore, let us say I have an active high decoder. So if this is A and B, I have a 2:4 decoder. Now I have 4 outputs, Y0, Y1, Y2 and Y3. What I can see is that I need the output Y equal to 1 when A and B are both 1. So therefore what I can do, I can simply say that Y3 is equal to Y. Because when A and B are 1, 1, Y3 will become 1 and that will be equal to Y. For all other times when A and B are not 1, 1, Y3 will be 0. So what you see is that we are in this case only using Y3 and remaining other lines are free. So if we want to realize some other function, we could do that. Although for the time being, let's not complicate stuff. There are lines which are not being used. We could use them, we could put them to some better use. So now, this is how we can realize this function using an active high output decoder. Now, how do you do this? Same thing using an active low output decoder. Same logic function. So let's call this as Y0, Y1, Y2 and Y3. Now things become interesting. One way to look at it is when we are looking at active low outputs. Let us look for those conditions when the output lines become 0. That's one way to look at it. Otherwise, what you can do is in this particular function, you are saying that for A and B, the only possibility where Y equals 1 is when A and B is 1, 1. So therefore, suppose we choose Y3 as our line of interest. Then what I can do, I can simply use a NOT gate and say that this is Y. Because when A and B are 1, 1, that time Y3 will be 0 and the NOT gate will convert it into the 1. However, However, this is one solution. This is fine. Now let us ask ourselves something else. That is, can we realize the function y using y0, y1 and y2? Let us again draw the same decoder with active low outputs. Now let us say I don't now care about y3. My interest lies in y0, y1 and y2. That means, can I use y0, y1 and y2 in such a way by combining them through some means to realize y? First thing to note is that y0, y1 or y2 lines will be activated when A, B are either 0, 0, 0, 1 or 1, 0. So this corresponds to each of the three lines, y0, y1 and y2. So when A and B are 0 and 0, y0 will be 0. Now when y0 is 0, what should be the value of y? When A and B are 0 and 0, y0 is 0, the value of y should be 0. When A and B are 0 and 1, y1 is activated. But what is the value of y? It is still 0. When A and B are 1, 0, y2 is activated. That becomes 0. y0 and y1 remain as 1. What should be the value of y in that case? It should be 0. So therefore, what we are seeing is that for the first three rows of this truth table, either y0 is 0, y1 and y2 are both 1, or y0 and y2 are 1, y1 is 0, or y0 and y1 are 1, y2 is 0. And in all of these cases, the final output y is 0. So therefore, now the question is, which gate should be used to combine y0, y1 and y2 such that if any one of these becomes 0, the output y should be 0? Well, the answer is an AND gate. But what we see is that while this AND gate will work when at least one of these y0, y1 and y2 becomes 0, we have to ensure that it is satisfied indeed for the fourth case also. So when A and B are 1 and 1, y3 becomes 0. And at that case, y0, y1 and y2 will all become 1. So therefore, in that case, y will become 1. So even that condition is now satisfied. So this is also a correct solution. This is also a correct solution. Is that fine? Now I can ask you the similar question. How using an active high output decoder and using y0, y1 and y2, we can have the realization of y? Well, it's definitely possible. Let's go in the same fashion. Let's draw a new diagram. So the y function would look like this. So if I now have my active high output decoder, y0, y1, y2 and y3. So now suppose I don't want to use the y3 line at all. So when a and b are 0 and 0, y0 is activated, y0 will be 1 and the others will be 0. When a and b is 0, 1, y1 will be 1, the others will be 0. And when a and b is 1 and 0, y2 will be 1. Now for these first three cases, y is always 0. So therefore now the question is, which gate should I use to combine y0, y1 and y2 such that when even a single one of these three becomes 1, the output will be 0. There is only one gate we know that does it, that gives a 0 when any of its inputs become 1, and that is a NOR gate. And that's it. This is how you can realize the y function as well. This is also a valid, accepted solution. Now let's take one more example. Let us say this is my function and I have a 2:4 decoder with active low outputs. So let us say now I hunt for the ones. This is y0, y1, y2 and y3. This is, let's say now we are looking again for the minterms like we used to do earlier while solving the K-maps. Now let us say that we are looking for these two terms. That is the cases when AB are 1, 0 and 1, 1. So when AB are 1, 0 and 1, 1, either y2 or y3 will be activated. So therefore, depending on what the value of A and B is, either 1, 0 or 1, 1, either y2 will become 0 or y3 will become 0. So when y2 is 0, all the others will be 1, and when y3 is 0, all the others will be 1. So therefore now, suppose I ask myself, can I use a gate to combine y2 and y3 and get the final output y? So the question now is that when we are looking at y2 and y3, we are essentially trying to get the value of the final y as equal to 1. So therefore, when any of the two inputs become 0, the output should be 1. So therefore, if I use a NAND gate, then it would work. But suppose A and B are now 0 and 0. If A and B are 0 and 0, y0 will be 0. And at that time, y2 and y3 will be 1. And when you get both ones at the input of the NAND gate, the output will be 0, which is correct. And when A and B is 0 and 1, y1 is 0, y2 and y3 are still 1. So therefore, this y will continue to remain 0. So even this condition is taken care of. Now, let us define one more output for the same set of inputs. Let's call this as 0, 1, 1, 1. Now using the same decoder, Can I realize the function z also? Yes, I can. I can, in fact, define one more NAND gate. And using the same logic where I'm looking for the ones, I can now NAND together y1, y2 and y3 together and get the z function. So this is one example where using a single decoder, I can realize two functions, not just one. So therefore, in some sense, decoders are even more handier than multiplexers. So one mux has one output, so therefore you can realize only one function using one mux. But since there are multiple outputs of a decoder, you can use them in any number and combination that you may like. And therefore, you can realize multiple functions. Now, let us come to the question, what is inside a decoder? Remember when we were discussing about multiplexers? After realizing what its capabilities are, we are still at the end of the day engineers, and we would like to find out in what manner the multiplexers can be implemented using gates, which we did. And now the question is, how can we design the decoder that is the inside of this trapezial or trapezoidal box? What is the circuit that converts A and B to y0, y1, y2 and y3? So therefore, let's take this example. This example is when I have an active low output decoder. So if I draw the truth table, in this case y0 will be 0, y1 will be 1, y2 will be 1, y3 will be 1. When A and D are 0, 1, this is 1, this is 0, rest will be 1s. And like so. So now, when we can look at y0, y1, y2 and y3 as 4 independent logic functions. Now what we are seeing is that the 0 is rare. So we can see that the 0 is rare not just in y0 but for all the y's. So we can actually use y0 as something like or all the y's as something like max terms. So therefore I can say that y0 in terms of max terms is A and B. So sorry, A plus B. This is how we write the max term for y0. Remember, 0 indicates max term and A0, B0 indicates no complements. Likewise, we can say that y1, this is 0, so A plus B bar. y2, A bar plus B. Finally, we have y3, that is A bar plus B bar. These are the 4 functions. Now suppose we have the inputs A and B and we can generate their complements using NOT gates. This is A bar and this is B bar. So y0 was A plus B. So therefore we can use an OR gate. and take the lines A and B. This is Y0. Y1 was what? Y1 was A plus B bar. So again we will take A and we will take B bar. Y2 was A bar plus B. So we will take A bar from here and B from here. And finally Y3 is A bar plus B bar. So both the bars we will have to now OR. So this is what the decoder looks like from the inside. These are what the logic, the internal logic for the decoder with active low outputs looks like. Similarly, we can also do the same for 2:4 decoder with active high outputs. Let's do this very quickly. Once we have done this, once we've done the active low part, we can do the active high part also pretty easily. So here Y0 will be 1, the rest will be 0. Here Y1 will be 1, next Y2 will be 1, finally Y3 will be 1. So we can say, just by looking at the minterms, Y0 equals A bar, B bar, Y1 equals A bar, B, Y2 equals AB bar, and Y3 equals AB. So very quickly we can just draw A and B and their complements. So A bar and B bar, we will need an AND gate. This is Y0. Then A bar and B, this one. Then comes A and B bar. Finally, we have A and B for Y3. So again, this is what the internal diagram for a 2:4 decoder with active high outputs looks like. So in this particular lecture, we saw the basic principle behind another MSI block that is called a decoder, which is an opposite of the mux or the multiplexer. So just like the opposite what we would expect, a decoder has multiple outputs for the same number of select inputs as that of a mux. So number of outputs of a decoder is equal to the number of data inputs of a mux. And what we saw was that decoders can be of two types, one with active high outputs, the other with active low outputs. And we can use the decoders to realize, in fact, more than one logic function output, because now for multiple outputs, you can combine them in any fashion and realize as many outputs as you would need. So therefore, the decoder is in some ways more powerful than the multiplexer. So in this particular lecture, we mostly stuck to the discussion about 2:4 decoders. However, you can also have 3:8 decoders, 4:16 decoders. So the notation for the decoder essentially involves number of select inputs to the number of outputs, just like the opposite of a mux. So in the next lecture, we shall look at certain other features of decoders which are analogous to multiplexers and how we can build more complex circuits using decoders. Thank you.